Okay, there's still plenty of stuff to go over for complex numbers, so this is not a total loss, right? And this is going to be the things that's our importance. I'll spend the last few minutes going over the complex plane again, because I suspect that that's not the most obvious thing to everybody, and it's just a good thing to know. All right, it's just a quick recap. All right, so complex numbers arise when we try to solve the equation x squared plus 1 equals 0. Yeah, I should give a recap. Thanks, Ben. Rather than assuming that this just doesn't have a solution in real numbers and moving on, we use wishful thinking and invent a solution. We say that I squared is equal to -1. And let's just also assume that I satisfies a bunch of nice properties that we would expect of real numbers. So it becomes pragmatic to graph things like this using the complex plane. All right. And visualizing stuff in the complex plane has a lot of nice implications. So for example, rotation. It turns out that rotation by 90 degrees is the same thing as multiplying by I. All right, so this is -4 plus 3i, and that's exactly what we'd expect. And rotation in general is also really useful with complex numbers. The reason is because every number can be expressed as r times e to the I theta. All right, and what does this mean? Well, theta is this angle, and r is this length. And when we multiply like r times e to the I theta by like, let's say, s times e to the I phi, we get another number that looks like the same thing. So what we see using this definition is that multiplying two complex numbers actually is like the same thing as multiplying their magnitudes and adding their angles. All right, great. Thank you, Eric, so very much for letting me know that we're not recording so that we can at least get something up there. So now we're moving to solving equations. So let me remove all of this and we can continue. So what are we going to do with this? So now from here, we go directly to x plus 1 is equal to 3i or -3i. So x is equal to, we can express it like this. So now we see that we are now able to solve any of these things using this method. And now since we can represent this number however we want, maybe using I, maybe not using I, we see that like every quadratic actually is going to have two solutions. They're either going to be, maybe they're going to both be real, maybe they're both going to be imaginary. And I get no. And what am I missing? X squared plus, I'm going to see x squared plus 6x plus 9. That's a good point. But a bit of a rabbit hole. We can say that like this solution counts twice because we have the squared here. All right, so yeah, I guess that's the sort of cheat way around it. So yeah, and counting x equals -3 as like two solutions, even though it should be one, is actually going to come up important in later. So every one of these quadratics, or in any case, every one of these quadratics does have a solution that we can express. Maybe using imaginary numbers, maybe we don't need to if we're lucky. Is anybody good? Is everybody good with that? All right, I have one yes. I would prefer to see more before I continue. Now I have two yeses. That's enough. So I want to throw a wrench into that. I want to look at this equation. And I want you guys to solve it, or just think about it for a minute. All right, well, the obvious answer is this. I find this to be really unsatisfactory. All right, because like we didn't even know what square root of -1 is, much less square root of I. So like what, are we gonna have to create an entirely new, are we gonna have to create a completely different number to solve this? Are we gonna have to like say like J is the meta imaginary number? Yeah, let me know what you guys think. How are we gonna resolve this? Should we just go ahead and create J and see what happens? All right, because I have no idea what the square roots of I is. All right, I want more people to All right, so a couple of people say yeah, a couple of people are saying let's do this. And I kind of want to do it just to see what would happen. All right, so J is the meta imaginary number now. All right, J squared is equal to I. J to the fourth is equal to -1. Nice. So let's solve this equation now. Are you going to create the meta imaginary number? And nobody's responding. So I hope you can all see that, yeah, this is like, this could go on forever. It's madness. All right, it's ideally, we'd want to like not have to do this. Like we want to be able to solve all types of equations. And it turns out that we actually can. All right, the reason that like I abhor this so much is that there's a much better way of writing it that doesn't involve like any square roots that we don't know at all. All right, and a lot of people are seeing what I'm going to go at. So to solve this, we're actually going to return to the complex plane. All right, let's guess that this is our number. All right, so we know that I is like e to the I pi over 2. All right, how did I get that? Oh, just a refresher. Well, this radius is 1, clearly, because we defined this length to be 1. And this angle is 90 degrees, or pi over 2. I'm going to delete that because that's illegal. All right, so we want a complex number that multiplies to this. So we see a lot of multiplication. So what we're going to do is we're going to say x is equal to r e to the I theta. So what does x squared look like? Rx squared is equal to r squared e to the I 2 theta. And that's equal to e to the I theta, e to the I pi over 2. So can we solve this? All right, if we do this, we're going to want to figure out what r is and what theta is. So first off, what is r? Like what radius makes sense? The way that we're going to want to do this is we're going to want to split these things apart, treat the e part as separate from the real part. So we can say r is equal to 1. Right, and it is actually convention for r just to be assumed positive. So this actually works fine. So now now the next question? What is theta? Oh, okay. So I see pi over 4 radians. And yeah, okay, so I'm going to have to like wrap this up pretty quickly. That's because I have to be in a meeting, but this is important. So I will stay for as long as necessary. So we think that theta is equal to pi over 4 because 2 theta is pi over 2. That makes sense. However, this is not the entire story. I'm actually missing something. And what I'm missing is the fact that like we can actually add 2 pi to this angle and nothing will change. So what I'm missing is 5 pi over 4. When I take 2 theta, when I take 2 theta, 5 pi over 4. I get 5 pi over 2, and that's equal to pi over 2. So we've just shown that there are 2 solutions. All right, this guy right here and this guy right here. And you can do some more work, and you can actually show that those are the only 2, but that's boring. So I won't worry about that right now. All right, and we see that these are like 45-degree angles. And we know the radius is 1. So that means that we can actually figure out what this is in normal form. All right, and it turns out to be root 2 over 2 plus I root 2 over 2. And this is negative root 2 over 2 minus I root 2 over 2. So yeah, it turns out this is really cool that we can express the square root of I as another complex number. So the square root of I does exist, and like we can find it, but we just don't write it like this. Write it like that, because at least like we know what it is. Yeah, so now whenever your algebra 2 teacher or whatever introduces the square root of -1, you can bamboozle them with the square root of the square root of -1 and get like this. So we can solve equations like that. And this actually leads to a much more general application. All right, and that is the roots of unity. Have any of you heard of the roots of unity? Let me know in the chat. All right, so I have gotten 2 yeses, and one of them was Ben. So I'm going to assume that this is a new topic. So what are we doing here? All right, we are going to be solving this equation. All right, and how are we going to solve this equation? All right, the solutions are going to be complex numbers. All right, so I'm going to I won't go into the process of like figuring out this. I'm just going to derive it. I'm just going to show you it and then explain how you might get to it. So I'm going to start by drawing the circle. And then from there, I am going to draw a polygon of all things. Let me make this thick again. So what is going on here? So what we are doing is we are making these angles equal. So this is 72, this is 72, this is 72, this is 72, and this is 72. So we can express this as x is equal to e to the 2 pi I over 5, or e to the 4 pi I over 5. And where am I getting this 2 pi over 5? That's just 72 degrees expressed in radians. So it turns out that these are the 5 solutions to x to the 5th is equal to 1. All right. Of course, what you do, like for x to the n, is you just replace this 5 to an n, and you just keep going forward. So now let's just think, why is this true? All right, well, let's sort of test it out. Let's pick e to the 4 pi over I over 5. And let's raise that to the 5th power. What do we get? E to the 4 pi I. So what is the radius of this? 1, of course. What's the angle? Well, we've just gone around the circle twice. We arrive at 1. So it works. And you can do the exact same process with any of these other numbers, and you will also see that it works. All right, so yeah, and again, we have seen why this radius angle form, this e to the I theta stuff is so useful. And that's because we can solve equations like this really nicely. All right, if you want, this actually even leads to a proof of the cosine of 72 or the sine of 18 or whatever equivalent you want, just by manipulating these expressions. And it all stems from the fact that this happens. So you see that we've used a lot of geometry here. And this is because complex numbers are really the bridge between geometry and algebra. And that's one of the huge reasons why it's so important. Just to wrap up quickly, this, I suppose, was like a shorter lesson, but this is only meant to cover the basics. And we do have a video for more advanced applications of complex numbers. All right, and the thing that I'm going to finish with is the fundamental theorem of algebra. I got a question. I have a quick question. E to the 4 pi I over 5 to the 5th. Well, it's just exponent rules. We just cancel these two out because we multiply these. But let's go to the fundamental theorem of algebra. So this is something that seems obvious, but is actually really hard to prove. All right. So every polynomial can look made to be looked like this. All right, and of course, these can be real coefficients if you want. And we know from our study of quadratics that we can factor any quadratic as like x minus r1 times x minus r2. All right, let's say like we want this to continue. So we have this. And why would it look like this? Well, there are n x's here, and the degree of this is n. So that makes sense. But there are n factors right here. And we know it's true for quadratics, but is this true for every polynomial? Does every polynomial have n factors? It turns out the answer is actually yes. And this is the fundamental theorem of algebra. And it's, why is it called that? This like grand sounding name? Well, it deals with the fundamental equation, the polynomial. And it basically just like destroys the whole thing because all of these have a solutions. All right, but we have already seen that sometimes we might need these R1s to be complex. All right, so like we can see that any real polynomial has solutions, even when they're complex. All right, what happens if R1 is equal to R2? Well, there's still different factors. So the way that we get around this is if like say we have like x minus 2 squared and like a bunch of other stuff, then we say that this solution has multiplicity too. All right. And here's the real magic of this, is that I actually made an assumption here that we didn't really need to make. Even if these coefficients are complex, we can still express it like this, as complex numbers. So I want to pause for a minute and just conclude on that and just think about like how like cool this is. All right, so for real equations, we couldn't solve all of them because we had to introduce complex numbers, right? Even like piddly quadratics. But now, when we're solving complex equations, we can still solve them using only the complex numbers themselves. So we don't need to add anything else in here. And it's that extra dimension that really allows us to do this. And I think that's really cool. So unfortunately, I have to leave now. I need to go to a talk. If you guys have any questions, Ben will be staying in here for a few. Ben can stay here for a few minutes just to answer whatever you need. And I will try and end this without ending the entire meeting. All right. Thank you all for coming. All right. Thank you all for being patient with us as we got this sorted out. And I will see you all the next time I teach.